Good afternoon. First announcement. So there were several students who had emailed me saying that they hadn't matched it. That's why quiz 1 and quiz 2 were reopened. So for the Gradescope submission, quiz 1, I believe, is open till tonight. And then quiz 2 was open until yesterday or till Monday. And so when students upload it, students must match their answers to the answer location. And all that is basically you select the answer and then you select which page it is on. If everything's on one page, you just select the answer, page 1, 2, page 1, 3, page 1. So all 10 of them, page 1. So it's basically 20 clicks that you have to do just to match it. Without matching it, the system, well, the grading would not work. Because if I type in any grades for, let's say, problem number 2, but if a student did not have problem number 2 in their answer sheet, system's not going to match it to anything. So if I would award points, system will not award any points to that response. Does that make sense to everyone? Right? So at the instructor end in Gradescope, I set up the points for the questions. Students end, you're just matching and just letting the system know where on your answer sheet it's located. That's all. Every single question requires 2 clicks. So if you have not yet done it, please go ahead and ensure that it is on there. This grading will begin shortly. So, all right. The other thing is there were several questions about the problems or the examples that are there on the slides. And so the request was to actually work through the actual problem so that students can see, view the steps, and then if you have any questions, you can ask them. So that's what I'm going to do today. Let's bring up the notebook. And yeah, that's the right one. So I'll work through all of these problems, and then you can let me know if you have any other questions. Okay, for the most part, all of these are based on Ohm's law and the power equation, V equals IR, and power equation P equals VI, right? So two loads or two resistances connected to one single voltage source. If it's one single voltage source and it's in parallel, that means the same voltage is applied to both these resistors. So we can calculate the power directly, or if you wish to apply Ohm's law, I can simply find the current I, let's call it I1 and I2 from Ohm's law. Okay, so here we are directly trying to find the voltage with the current 8.3 is determined from Ohm's law. Since both are the same, I would say I1 is equal to I2 is equal to V over R, which is 12 over R. Now, and you perform this calculation and you would obtain this value 8.3. Okay. Everything again, and I have stated this earlier on, and I'm also restating it again. All circuit analysis techniques are just based on 3 laws: Ohm's law, KVL, and KCL, and that's it. Any and all circuit analysis techniques are derived from these 3. So in this case, you're simply first applying Ohm's law to determine what the current is. We could also apply the combination of Ohm's law and the power equation to determine the power directly, which is what's done here. So for power consumed by each load, what we are doing is we know R, and so we can write P is equal to V square over R, which is 12 square divided by 1.44. 144 divided by 1.4. Okay. Okay. And because both resistances are the same, that means the power absorbed or received by both resistors is the same. And so it's 100 watts, 100 watts each. Total is 200. The other way to find it is to find Req of the parallel network and then apply Ohm's law or the power equation to the Req, the total equivalent resistance. Okay. And that comes just a couple of slides later. So 8.3 amps and 100 watts. Now, because they're in parallel, the voltage is the same, but each one of them is going to draw current from the source. As long as the source is capable of supplying that current, it's going to be double. You connect a third resistor in there in parallel, there's 3 times 8.3. Fourth resistor, 4 times 8.3, assuming they're all the same, of course. All right. So what the source is seeing, is that the total combination of all 2, 3, 4, or 100 resistors connected in parallel. Right? The source does not know how many are connected. It's not a sentient being. It's just seeing one single equivalent resistance. And one single equivalent resistance is the parallel combination of those resistors. And so we can find the total current from the source by applying KCL. Right? We apply KCL either at the top or at the bottom, and we can find the total current that's being pulled from the source, or we can just find from the total power 200 watts. So total source current can be found from KCL. And I'm just going to say IS is equal to I1 plus I2. Typically, when I apply KCL, all I do is I sum up all the currents that are entering a node, and I equate it to the sum of currents leaving the node. In this case, IS is entering the node, and I1 and I2 are leaving the node, going to the resistors. You can also find it from this step right here, because I know total power, P total, is 200 watts. I can find it from the applied voltage and R total. Okay, so I can find Req from there, and I can find A square times R total. Okay, so all of these equations are straightforward. You're all familiar with this. You can also solve this in any manner. So almost all of you have confidence that you can do this. The thing I'm trying to show you here is these three equations, these three laws, Ohm's law, KVL, KCL, they are tools for an electric circuit analysis. These are tools. One is a screwdriver, the other one's a spanner, the third one's a wrench. And you can use these three tools in any order and in any combination to perform a variety of tasks. So you could solve a circuit by applying Ohm's law and KCL, then you apply Ohm's law again in succession to find different quantities. And there are multiple pathways to solve the same circuit. Okay, so the more you practice, the more innate it becomes. Right? You can take the same circuit and you can solve it in a variety of different ways, and that will enhance your circuit analysis skills, circuit analysis techniques. All right, let's take a pause. Let me know if you have any questions, and then we'll move on to the next. I'm just going to spend just a few minutes on those. In your physics classes, do you go in depth? How far in depth do you all usually go? Yeah, with these kind of analysis. Was it a long time ago, the physics class? Yeah. Well, wasn't it in the first year? That was just last year, right? Yes, go ahead. Okay. Okay. And we'll get to those two later on in this course. Yeah. Okay. All right. So what resistance does the source see? Well, it's R by 2 because it's in parallel. All right. Series, the same thing. Series circuit. You're applying 12 volts. Well, now current has nowhere else to go except that one single pathway. And because it's that one single pathway, we can again apply a combination of techniques. Okay. There's voltage division that we can perform. The voltage division is derived from Ohm's law. It's a shortcut. And we'll talk about that later on. But that's just a shortcut technique that is derived from Ohm's law. Fundamentally, if I wish to apply Ohm's law here, what do I do? Excuse me. I want to find the current I, right? This current I. So if I want to find the total current I, you add up both resistances. But now the thing is, how do we know that we should add up these resistances? That itself is also derived from Ohm's law. Okay, so everything again is derived from Ohm's law. So here, current flows in that same direction. So total current I is V over R total. Okay, and V in this case is 12 volts, and then R total would be 2.88. Okay, so this gives us 4.17 amps. 4.17. Again, just an application of Ohm's law gives us 4.17. From there, of course, we can find power for each resistor. This is V squared over R, or I squared times R. And as far as circuit analysis goes, these problems are rather straightforward. So you should, even for larger circuits, but even for smaller ones, you should develop the habit of solving them with all possible equations. So you do V squared over R, and you do I squared times R. Total power in this case, because the resistances are the same, you can apply 12 square divided by 2.88, right? So you can get, let's do, if I was to do total power, I can do V square over R total. Or I can do I squared times R total. Okay. And then you should, of course, obtain 50 watts. And that's the total power being delivered by that source. Okay, 50 watts. And for each individual resistor, once you have the current that's flowing through there, you simply apply this equation and you can find the individual power for those individual resistors. Now, without knowing anything about circuit analysis, okay, you have the series combination of resistors. So in a series combination of resistors, what can we say about the current? Current is the same. And again, same statement for parallel, voltage is the same. So in a series circuit, the current is a result of all of those components, meaning all of those resistors working together. Hence, it has the same value. Okay. So if the current is the same, that means when we apply Ohm's law to these resistors, V equals IR, if I remains the same, and then R also remains the same, that means the voltage that appears across each resistor is also the same, right? Mathematical terms. Logically, we already know, if you study this from physics classes or any other class, we know same resistors, meaning the same power and same voltage, right? The point here is in a series circuit, current remains the same, but the voltage gets divided across each one of those resistors. And the voltage that appears across each resistor is directly proportional to the value of the resistor. The higher the value of the resistance, the higher the voltage drop. The lower the value, lower is the drop. Make sense? Now you have two resistors in here, you know voltage is being divided. Values of both resistors are the same. And there are only two of them. That means logically the voltage is being divided into two equal parts. Make sense? And 6 volts. And mathematically, you can prove it and you can calculate it, of course, using Ohm's law. If it was three resistors, all the same value, three equal parts. 100 resistors in series, all the same value, 100 equal parts. That again goes back to this example of light bulbs in series. If you have 120 light bulbs in series, all of them with the same resistance, then 1 volt will appear across each light bulb. Okay. So voltage that appears across a resistor in series connection is directly proportional to the value of that resistance. All right, let's take a pause. Let that sink in. Let me know if you have any questions. All good? Okay. All right. Single current source applying two loads, same series connection. So if it's a current source, the same current flows through both resistors. That means if I wish to calculate the voltage drop, VR for each individual resistor is simply I times R, 8.3 times 1.44. That gives us 12. And because it's two resistors, that means there's a voltage drop of 12 across both, and they would be in series. If you measure both voltages, you get 12 plus 12, 24. 12 times 2, 24. Same concept as the previous one. Previous one, we had a voltage source. Now you have a current source. But again, application of the techniques and the laws remain the same. Two voltages in series. And so total of 24 volts will appear across that current source. All right. And then each load, we can calculate again power for each resistance. PR is I square times R, or it is V square over R. We found the voltage as 12 volts. So it'll be 12 square divided by the resistance, 1.44. We still obtain 100 watts. Okay. 100 watts. So whether you do I squared times R or V squared or R, you still get the exact same value. Okay, how about the last question? What happens if you have a string or basically a series connection of 100 identical 1.4 ohm resistors? Let's start with two. If single resistor is 100 watts, how much for two? I know this was a long time ago, back in elementary school, but I'm confident you can get it. How much? Speak up. There's no penalty for speaking up. If one resistor is absorbing 100 watts in the series connection, how much for two? 200, yes. So if it's 200, how much for three? So how much for n? N times 100, right? So n times 100. As long as that current source is capable of supplying that much power, okay? All supplies have a limit. So the benchtop supplies that we have in the lab benches and all the labs around the building, they have an upper limit. It's about 30 volts in 3 to 5 amps, I think, maximum. So I would say around 100 watt supplies or 150 watt supplies. So depending on specification for the benchtop supply, it can provide any combination of that number. As a real life example, you might have, nowadays, there was a big push for consumer devices to go into USB-C power delivery. So it says USB-C PD. Okay, so real life example, USB-C ports. And power delivery. What is the standard voltage for a USB power outlet or a USB port? Absolutely right. Standard USB port is 5. The first USB ports were A and B, type A and type B. Then came along mini USB, and then came along micro USB. And then they came up with a third one, which was reversible, which was USB-C. Okay, USB-C is now the de facto standard. Right, so pretty much every cell phone, every laptop nowadays comes with USB-C. The reason is they had a future plan for using USB-C for everything, for power delivery, for video, for data connections, for all of it. Okay, so it's a one standard single port for everything. With power delivery, depending on the wattage, USB is no longer restricted to only 5 volts. The USB A and B is 5 volts. Standard smartphone chargers, USB-C, are still restricted to 5 volts, depending on the make and model of your device. But if you connect it to a laptop and you have a power delivery adapter, it can deliver a combination of voltages and currents. So let's say, for example, you have a 100 watt charger, 100 watts, and let's say your device requires only 5 volts. So what is the maximum current your device can charge at? 20 amps, absolutely. So now if your device is capable of charging at 20 amps, which is a huge amount of current, by the way, it's a lot, okay? That's basically a fast charger. Okay, that's a fast charger. So 5 volts is standard, but the amount of energy that can transfer, amount of power that can transfer would depend on that current. So If your device is designed to absorb large amount of current, it can charge far quicker because a large amount of energy is coming in. But now, instead of charging a smartphone, you charge, let's say, a tablet. And your tablet, just maybe it's designed to take up to 10 volts. So what is the maximum current it can supply? 10. And laptops typically take about 18, 19, or 20 volts. So if you're charging a laptop with this, 20 volts, your current is now 5 amps. Okay. So in your laptop adapters, you will have a specification. Sorry, not laptop adapters. On your laptop itself, there'll be a specification. On the label, it will say DC input. It'll tell you the voltage, 20 volts, let's say 5 amps or 6.5 or something. That'll be the maximum limit it can take. All devices have it on the label. Okay, so next time when you all have your laptops, you can just flip it around. You can take a look at the label if it's there on the back. It'll tell you. There are many smartphone companies that have, and I think I probably gave the example of my phone. My phone is not from the US. It can go from 0 to 100 in 20 minutes because it has a 120 watt fast charger. So it can absorb a large amount of power in a very short period of time. And so that's the principle. But again, if we tie this back to our circuit analysis, same principles, Ohm's law, KVL, KCL, and power equation. That's what it is. Okay. All right, let's take a pause. Let me know if you have any questions. For those of you who did look at your labels, do you see anything? 20 volts and 5, so 100 watts. Yeah. And it should say the same on the adapter, or the adapter could sometimes be rated for higher power, meaning instead of just supplying 20 volts and 5 amps, it could be capable of supplying 20 volts and 6, 7, 8 amps. It's possible. Yes. 48. Yeah. So there's a combination. As I said, there's a multiple combination of that voltage. That's what I have. That's what I have on my phone. So it just charges at a higher voltage. Yeah. Higher voltage and a combination of, it could be any so as I showed here, it could be any combination of voltage and current. So thank you for sharing that. I thought it only went up to like 25 or 30. 48 volts. So the comment being made is that USB-C can now, USB-C power delivery specifications can go up to 48 volts. It'd be interesting to look at what the max current is on there. So still 5, 48 times 5, 96, 96 and 96, 192, 192 plus 48. That was 192 plus 48. 230 watts, 240 watts. How much is your adapter capable of supplying? Does it say 20 and 5? 135. So it can probably supply more than 100 watts. That's an interesting thing. So the device's requirement is 100 watts. Okay. But now the adapter says it can supply more than that. So what do you think happens? So the device, the example, the real life example is device is rated for 100 watts. And 100 watts is 20 volts and 5 amps max. Okay. 5/6.75. Okay, 5/6.75. So let's break it down and let me explain what it means. So 20 times 6.75 would be 120, 15, 135. Yeah, that's why our adapter is for 135. You said 135 watts, right? Yeah, 135. So device is rated for minimum 100 watts, 20 volts, 5 amps, 6.75. If I translate this, that means the device is capable of charging or operating with a 100-watt charger or a max of 135 watts charger. Okay. So if you have a smaller adapter and you wish to charge your a device, it would still work. If you go any lower than that, it may perhaps not work. So I have my laptop is 15 years old. It's more than 8 pounds, huge battery and a brick of a adapter. Requires about a 230-watt power adapter. Okay. If I use a smaller adapter in there, it won't start up. It'll say, warning, charger, I mean, the adapter connected to the laptop is lower wattage. It cannot proceed. So it won't work. So there's a minimum rating that it needs in order to function. So if you go lower than 100 watts, it may not charge. Okay. So now what happens? The question is, what happens if you have a 100-watt charger? Sorry, a device that only not accepts, but is only capable of receiving 100 watts and not more. But if you now connect a 200-watt charger to it, you're sending a whole bunch of power through it. What happens? Will the device blow up? If the device doesn't have any protection built in, yes, it will blow up. That's when you get bloated batteries. The battery has a capacity to only absorb so much power. You send a whole bunch of power in there all at the same time. And the battery, once it gets full, you're going to charge and then it becomes bloated and swollen. That's when it would explode. Okay. So every single device comes with that warning. Do not use any other charger other than ours. There are two things for it. One thing is to make money. The other thing is safety related. Right? Because if they sell their own chargers, they're making more money. The other thing is actually safety related, because every device has a signal. Once it's full, it'll send a signal, say, stop, I'm full, I don't need any more energy, I don't need more power. It will shut off the charging. So if you use like a really cheap or generic charger, then it may just keep feeding it into the device and then batteries become swollen. I've actually had that happen to me inadvertently. I had one of those power extension, it was not strip, but it was like a splitter, electric power splitter. You plug into the wall, it came with USB ports. And because it was USB ports, I just assumed it's standard, so I plugged in my phone to charge in there, but it was new. I had no idea about the specifications. Phone became 100%. I just left it on charging. I didn't realize the charger never stopped sending power. Battery was swollen because it never stopped receiving charge. Anyway, those are all real life examples. All right. Single current source supplying two loads, but now the loads are in parallel. They're in parallel, still the same values. What do you think happens to the current in parallel circuits? Current gets divided. In a series circuit, voltage gets divided. In a parallel circuit, current gets divided. Voltage remains the same because there are only two nodes in a parallel connection. Okay. If there are only two nodes and you try to measure the voltage between those two nodes, it's always going to be the same. Hence, in a parallel connection, the voltage remains constant, the current gets divided. Okay. So the voltage is constant. We can find voltage by applying Ohm's law. So V would be equal to I times R total. R total. Okay. R total. R total for this is, of course, two resistors connected in parallel. And so it's the reciprocal of the sum of the reciprocals. 1 over R1 plus 1 over R2, the reciprocal of that sum. Okay. And that, again, is derived from Ohm's law. And we'll just go over that in a little bit. So R equivalent is 1 over R1 plus 1 over R2, and the inverse of that. And once you have that, you apply Ohm's law, and you obtain 6 volts. Okay, 6 volts. Just as the previous circuit where you had two series connections, and the voltage gets divided exactly equal parts. Same thing with current. You have parallel connections. Current is being divided into two exactly equal halves. And so it's simply 8.33 divided by 2. If you have 3 resistors, it would be 8.3 divided by 3. If you have n equal number of resistors, it would be 8.3 divided by n. So for n resistors in parallel, the current I would be equal to 8.3 divided by n. And that's what we see here. And of course, once we have the voltage or the current in there, then we can apply P equals V squared over R, or I squared times R. Okay. All right. Any questions before we move on? Okay. All right. So here is a summary of all our findings for all the 4 circuits. This is a voltage source with 2 resistors in parallel, voltage source with 2 resistors in series, current source with 2 resistors in parallel, and current source with 2 resistors in series. It's critical to understand that the small difference between a voltage and current source results in a big difference in the total power capabilities. Okay. If you have 2 resistors in parallel and you're connecting it to a single voltage source, and the current is being divided, meaning your source must be capable of delivering that power. Okay. If it's not capable of delivering that power, then the power is reduced. I'll give you again a real life example. There are rechargeable lithium ion batteries that are available in the market. That's been available for a few years that have built-in USB ports. Okay. I have several of those, like AA and AAA batteries that you can simply connect to any USB port. Has anyone ever seen those? No? Some of you have. So a pack of 4 AA batteries comes with a single splitter cable. So one end is a standard USB connection, and the other end is like a micro USB or USB-C that plugs it directly into the AA battery. So it splits into 4 parts. So you have let's say a AA or a AAA rechargeable battery. And instead of using a special charger for it, all you got to do is use that cable, plug it into any USB port. So I have several samples dating back from a few years ago. One of them had micro USB, another had USB-C, another one was like a flash drive. You literally just took the cap off and you plugged it into a USB port. Let me show it to you, since we are on that topic, and it's a real life example. So, as with all things, unfortunately, let's go to Amazon. And let's look at this one. Oh. There are plenty of these, okay? And they're it's amazing how inexpensive they have become. All right, so you have these, and you see this cable right there. Now, at one end of this cable, you see a USB. So I'm going to move my mouse. Let's just make it bigger. All right, so you see one end of the cable is a standard USB port, like right here. You see that? It plugs into any USB charger. You can plug it into your computer and it will charge. But at the other end, you see there are 4 outputs. So what is happening electrically? You're taking that one USB out on your charger or on your laptop, and you're feeding it into 4 different batteries. So all batteries are connected in parallel. What happens when they're all connected in parallel? They all receive 5 volts going into the battery. But now the current requirement for each battery still remains the same. If you connect it to a, let's say, something like a 100-watt charger, maybe it's capable of supplying a high enough current to satisfy all 4 of them. But if you connect it to a laptop or a desktop, which I would not recommend that you do, just in case something goes wrong, you don't want it to fry your expensive laptops. So always connect it to a standard charger. A charger blows up, it's okay, you can buy a new one. So if you connect it, let's just say you connect it to a computer's USB port, what happens? You have 4 devices all connected in parallel to that same power source. A computer cannot supply more than 0.5 amps of current from its USB port. It's limited to 500 milliamps. Okay, the standard USB ports that you have on a desktop or you have on a laptop, it's only limited to 500 milliamps. So now your batteries, which are the loads, those are connected in parallel, and each one of them is only receiving 1/4 of 500 milliamps. If you charge one battery at a time, it's going to charge faster. You get the entire 500 milliamps all to itself. If you charge 2 in parallel, it's 500 divided by 2. 3 is 500 divided by 3, and 4 is 500 divided by 4. So it's going to charge. It will work, but it will work very, very slowly. If you take a standard USB charger, like for your cell phone or your tablet, it's going to charge faster because a cell phone or a tablet charger can supply at least 10, 15, or 20 watts. Okay, even though all of these loads are connected in parallel. Does that make sense to everyone? And that's what these are. You simply plug it in. There, standard USB port, charger, and goes to all 4 of them. There's also a built-in circular LED light on top. When it finishes charging, it's green in color. So while it's charging is red, otherwise it's green. AA USB-C, that's all USB-C. There's another one that I haven't seen. Let's see, let me see if I can find it. Oh, these ones. There you go. Like a flash drive, simply unplug the cap and you plug it into a USB charger and it works. But what I found is the capacity of these batteries is slightly less. Okay, it says 1.5 volts, which is standard obviously, but it is only 1850 milliwatt hours. So the capacity is slightly less. And I wouldn't even trust 1850. Okay, 1850 is the capacity, meaning if you use up 1.85 watts from this battery, it's only going to last you 1 hour. Okay, again, remember milliwatt hours. So it's watt hours. Watt hours means if you use up 1 watt out of this capacity, it's going to last you 1,850 hours. If you use up 1,850 watts, or sorry, not watts, 1.85 watts, then it's all going to be gone in 1 hour. Okay, so the capacity is less. This one says, let's see, what does it say? Doesn't state the capacity. Oh, yeah, right here, 2550. And again, I wouldn't trust it to be exactly 2550, but logically it makes sense. These devices do not, the space is more. There's no USB port on these, right? So USB port takes up some space, and so the capacity is less. So anyway, next time you're in the market for rechargeable batteries, you might want to take a look at these. Fancy. All right, let's get back to our technical stuff. So there are AA or AAA rechargeable batteries with USB ports. All are connected in parallel. Same 5 volts as input. Current is added up. So source current is split between the 4. By the way, everything that we talk about in class or in the lecture, whether it's an example or anything, it may show up on a quiz or a final exam. Okay. And as I said, just looking at circuit diagrams on paper or on the screen may seem boring, but every concept that you're looking at applies in real life with real life examples. Okay. This is, we are applying a voltage source divided between 2 resistors in series. Let's see, real life example would be a solar cell, but that's actually generating. This I can, we can spin it the other way where we combine voltages in series to actually have more of a voltage output. Trying to think where I can use an example of a charger, older chargers. So yes, go ahead. Oh, same 5 volts as input to the batteries. Sorry. Same 5 volts as input to the batteries. I have a, yes, go ahead. So the question being asked is the 4 that were all connected, the 4 batteries connected in parallel, would they all have the same amount of power? The answer is yes. The caveat is that the source must be able to supply that amount of power. So let's say each battery is applied 5 volts. Obviously, it's a 1.5 volt battery, so there's a charging circuitry inside each battery. But let's say it charges max at 1 amp, just for simplicity's sake. So if it's 1 amp, so it's 5 volts and 1 amp, that means 5 watts is required by every battery, right? So it's 5 watts required by every battery, and all 4 batteries connected in parallel, meaning 16 watts would be required from the source. But if your source adapter is not capable of supplying 16 watts, then it would not work. It just charges very slowly. Yes, they will each get the same amount of power. So if it's 1 amp coming in, let's say if it's a 4-watt charger, 4-watt charger, if it's a 5-watt charger, that means it's capable of supplying up to 5 amps. So it'd be 5 amps divided by, sorry, not 5 amps, only capable of supplying 1 amp from the port. So 1 amp gets divided into 4 equal parts. So every single battery will get 250 milliamps, right? Only 1 watt coming in or 1 amp coming in. So in this case, we have to look at both the source as well as the batteries that are connected. Okay. It's 2 o'clock, so if you want to leave, you can leave. I'm just going to talk about this older charger. So I have many different battery chargers collected over the years. One of the battery chargers I have is nearly 20 years or probably even older than 20 years. That charger could charge up to 4 batteries at once, but it was split in half. Okay, so it was split in half, meaning you could charge 2 batteries at once on one side and 2 batteries at once on the other side. But when we inserted the batteries in there, they had to be in series. So I had a charger. Specification was AA batteries or 4 AA batteries. And the structure was such that you had to have 2 AA batteries in series in order for it to work. Meaning the charger was sending out 3 volts and charging 2 batteries at once. If you connected one single battery in that pathway, it would not work. So the circuit was exactly as shown here. You had a battery charger that was sending out 3 volts and was connected to 2 batteries in series. Okay. And that's how it was working. So that was a real life example. Now, of course, there are chargers and smart chargers that you can just charge single batteries at a time. Okay. And then current source works the exact same way. Right? You have a current source with REQ, either 2 connected in series or 2 connected in parallel. But you can see the difference in the power for all 4 right there. Okay. When it's a current source and you connect it in series, total power required is going to go up. It's connected in parallel. Depends on how it's connected, of course, in parallel. Again, power requirement could go up or down, right? But everything is dependent on what the load requires and what the source is capable of. Yes. Yes. For real life examples, yes. 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 The comment being made or the note being made is the difference between the real life example and the theoretical circuit analysis. So this is theoretical. So every analysis we perform, we are ignoring real life constraints, right? We are ignoring real life constraints. But this is important because when we are designing real life systems, we have to consider what it means, right? And so, but for theoretical analysis on paper, we ignore constraints. Unless it's, of course, explicitly stated in there. Yes. This one? Oh, the red and blue. Oh, yeah. So you're asking, the question being asked is about these, right? Yeah. So these are basically telling us, or was indicating that the total power that is being delivered by the source has now doubled. So it's going up. If it was only one resistor in not parallel, but yeah, being applied to that voltage source, then it's V square over R. But now it's V square over R times 2. And so the total power that is required or delivered has gone up, right? When it's connected in series, well, when you connect it in series, what happens? Voltage remains the same, but now current goes down. because the resistance, the effective resistance has increased. It's R1 plus R2. So now when you do V squared over R, we get V squared divided by 2R, so it's half. So in a series circuit, if you connect a series combination to a source, then each load only gets half the total power, right? Now, if you connect it in parallel like these, then each, assuming the source is capable of supplying the maximum power for each battery in a real life example, then the total power is now double, right? So 4 batteries, it's times 4, assuming the source can supply. 1 battery, X, 2 batteries, 2 times X, 3 batteries, 3 times X. So when you have a parallel circuit, it pulls twice as much power from the load. When you have a series circuit, each component only gets half of that power. And same thing with the current. If you have a current source, total power is half when it's in parallel. And when it's in series, again, the exact opposite of a voltage source. Okay. With batteries, it's easier to, it's with a voltage source, it's easier to explain because you have real life examples of batteries, and batteries are voltage sources because it can supply a constant voltage. Hence, it's a voltage source, supplying current also. But current sources, like benchtop supplies, the benchtop supplies can run in constant current mode. So not as many real life examples. Okay. All right, we'll end class here today, and we'll pick up here again on Friday. How many of you are going to buy those batteries now that you've seen them? Yeah, because everything is like embedded, right? Yeah. I'm still, I don't get rid of anything. My limited stuff, but once I have it, if it's working and running, then I just keep it. It's in the collection, yes. All right.